Hello. Let me begin by apologizing for the poor quality of the scan. So here I want to talk about the notion of capacitance. So it's probably a good thing to point out because this is true, but it's not always obvious to us that the conductors are also charge reservoirs. They can store charges not in the interior, but certainly on the surface. For example, in this fashion, and they can be charges can be either stored or later drawn out for commercial and then engineering use later on. So it's pretty practical, a pragmatic concept to know how much charge can be held in a given conductor at a given potential. Uh, so that's where the concept of the capacitance comes in. And the first observation is that everywhere inside the conductor is a constant potential or equipotential. Say, let's say the potential V. So the same potential has to be maintained throughout the entire body of the conductor. And that's just a consequence of the fact that there can be no electric field um, within the body of the conductor. And, and that includes the surface as well. So you can think of the surface of the conductor as some sort of a equipotential contour, let's say at the potential V. And as you move far away from such a conductor, obviously the potential drops to zero eventually. Um, so this is so all of these things I've just said are just very generic behavior of any conductor. In fact, um, now let's think about applying the Gauss theorem to this imaginary surface, just enclosing the given conductor, and see what sort of results we can draw from it. And the electric flux, as computed by this surface integral, will be equal to the total charge inside that surface divided by the dielectric constant. And this surface, as I said earlier, can only reside. This charge, as I said earlier, can only reside on the surface of the conductor like this. And and the potential starts out by being at some value of V, and then drops down gradually to zero. Um, then the basic linearity of the electrostatic relations and Maxwell equations in general says that if you double the value of the potential, then you also double the charge. So there has to be some sort of linear relationship between the potential at the surface of the conductor and the charge that accumulates at the surface of the conductor. Um, and therefore, you can define the ratio of the charge to the potential, which, as you can see from this general expression, will be given by this integral. So here, phi tilde is a normalized potential, um, which does not depend on the exact value of the potential on the surface. And therefore, what it implies is that this integral will not depend in any way on the exact amount of charges or exact value of the potential, but rather it's measuring some sort of intrinsic feature of the conductor itself, or it just measures the geometric property of the conductor, such as the shape and the radius or the size of the conductor, for example. And so here the lesson is that once you know how to compute this capacitance, then under any given situation, if the conductor is held at say 1 volt potential, then you can exactly know just how much charge has been accumulated on its surface. Okay, and so we're gonna try and compute that in the case of a spherical conductor. It's quite easy for that case to compute the capacitance because we know exactly what is the potential function as a function of distance. It's exactly the same as that of a single point charge. Um, and from this formula, we can also see that right at the surface of the sphere, we have this potential, which is what we used to call the potential V. So another way of writing down the potential of a spherical conductor is in this way. So it's the surface potential V multiplied by the radius of the sphere divided by the distance. And therefore, this Gauss integral works out to just 4 times the potential times the radius of the sphere, that in turn equals the total charge divided by the dielectric constant according to Gauss theorem. Now, by taking the ratio of Q to the V, we arrive at the expression for the capacitance for a spherical conductor, which is 4 pi epsilon times R. So it's a general feature of any capacitance that it has to have a physical dimension of dielectric constant multiplied by the physical dimension of length. So the fact that it comes out as proportional to the radius of conductor of the sphere is not surprising at all. And that also runs in line with the intuition that if you have a big object, then it's likely to hold more of anything, including the charge. So if your sphere is bigger, then it's probably going to hold more charge on its surface. And so maybe what's slightly non-trivial is that the capacitance does not grow as the square of the radius, which you might have imagined from the fact that the surface area scales as the square of the radius, but rather it scales linearly with the radius. And that's really dictated by the dimensional analysis consideration that the physical dimension always has to be linear in length for the capacitance. Now, once you have this result at hand, you kind of feel tempted to apply this result to the case of the Earth. After all, the Earth is a sort of a sphere, and it's sort of a conductor as well. So if you apply this naive model to the entire Earth as a spherical conductor, then the capacitance of the Earth is just this thing. But the R is the radius of the Earth, which is a huge number. So basically, you can treat the Earth as a conductor or capacitor with pretty much infinite capacitance. Okay, so obviously I said it wrong here. It's not resistance, but capacitance. Sorry, I should have said a radius, not resistance. What about the potential? Well, the potential of the Earth on the surface would be inversely proportional to the radius. And since the net charge of the Earth is zero. I mean, we know that Earth is overall a neutral object, and therefore the potential on the surface of the Earth is zero. And now the interesting situation is when you happen to ground, when you happen to connect a ordinary metallic sphere, let's say you have in your at home or in your lab, uh, by a piece of wire to the Earth. Uh, Such a procedure is commonly known as the grounding, and and what happens in physical terms when you ground something to Earth is that you're basically taking this object you're grounding to be at the same potential as the Earth surface. Because once you connect two objects by a wire, then the two objects um, must be at the same potential. And if they're not, charges will continue to flow until the two objects are guaranteed to be at the same potential. So that's something that must happen. And since the Earth is at potential zero, and connecting a tiny object, certainly tiny compared to the size of the Earth itself, is not going to change that. So then, as a result, the potential of this object, whatever that is, has to equilibrate itself with the potential of the Earth, which is zero, and that means the potential has to be zero for this object as well. Now, if you invoke this relation that we have just derived, Q equal to CV, and V is zero for this object because it just got connected to the Earth, it implies that the charge on this object also has to be zero. That means if initially this thing was charged with some charge Q, then this extra charge will have no choice but to flow into the Earth and evaporate basically. Okay, and that kind of guarantees the safety of this object as an electric instrument, for example. And this is probably a familiar scene in many households, I hope. Okay, so the other theme that I want to touch upon today is the notion of the capacitance matrix. Um, Thus far, we were only talking about the capacitance of a single object. So if some object, a metallic object, is held at a potential V, it implies that a certain amount of charge has to accumulate on its surface. And the linear relationship between the charge accumulated and the potential at which it was held is the capacitance. But now we can generalize this consideration to the case of many metallic objects or many conductors that are close by, at least close enough they can effectively interact with each other. So now you can endow each island of conductor with its own charge and its own potential. And think about whether some relations can exist between them. And as a general rule, this relation exists. I don't think I will necessarily derive this relation. It can probably derive from the underlying electrostatic relations, but you might as well think of this as an empirical rule which exists, firmly established. And what I would rather do is to explore the physical meaning of this relation. So what this relation says is that the charge accumulated on any one of these conductors, let's say Qi, is the result of the potential not only on that island of conductor itself, but it's also a consequence of the potential of the other islands. Okay, that's what this off-diagonal capacitance Cij implies physically. So, for example, if I hold this this particular island at zero potential, then the first relation would say there will be no charge induced on that island. But even if this island itself was at zero potential, if I could just raise the potential of some nearby conducting island, then that action of raising the potential on the nearby island will influence the status of this other island and induces some charge because of the interaction between the two islands. So another way of understanding this complicated relationship is to consider the case where only one of the islands is held at some potential. Let me call that potential value equal to 1. And all other islands are held at zero potential, like this. Okay, and because electric field lines will flow from the high potential region to the low potential region, we might as well expect these field lines to look something like this. So all the arrows are pointing away from the high potential island, and they're flowing into all the islands that are held at zero potential. And now from this picture, you can pretty much convince yourself that if you draw a Gaussian surface around one of these islands at zero potential, then there will be a net influx of electric field, right? It's clearly not going to be all coming out on average. Rather, there will be all going in on average. And according to Gauss' theorem, that implies that the charge sitting on the surface of these islands will be negative. Now that implies that this particular capacitance value of C31 will have to be 0. Okay, so C31 will come in when Q3 is on the left-hand side and phi1 is on the right-hand side, and they're related by this number, which is C31. And the fact that the phi1 is held at a positive potential, however, the charge induced on the island number 3 is negative, implies that these capacitance value has to be negative. And you can prove this as some sort of general mathematical theorem that if I not equal to j, then Cij has to be a negative number. It's also clear that the self-capacitance Cii has to be positive. And you can also prove that if you sum the Cij over all the j's, so it's a sum of the self-capacitance Cii plus all the rest, which are called the mutual capacitances, then that value better be positive. Okay, that's also something you can prove, but it should also be more or less obvious on intuitive grounds. Okay, and the other thing I forgot to write down here is that these capacitance matrices are always symmetric. So Cij, whatever it is always equal to Cji. So if you think of this Cij as kind of a matrix, then it's always a symmetric one in that the off-diagonal entries with Cij and Cji are always equal. And that's also something you can prove on by invoking Green's reciprocity theorem, but I think it's okay for us to just share this as some information we can take for granted. You're certainly welcome to look up the textbook for in case you're more interested in the proof of that statement. Um, the final aspect of this situation that I want to emphasize is so far I have only considered the situation where only one island is at non-zero potential and all the other islands are at zero potential. But the general situation is when every island is at some non-zero potential. So why don't we analyze that? Well, it turns out that it's not really necessary to go into that general situation directly because all we have to do is to consider cases where only one island is at non-zero potential and everything else at zero potential. And once we understood what's happening in each of those cases, then the general situation is nothing but a linear superposition of those cases we have just considered. And so by taking advantage of these principle of linear superposition that works across the entire spectrum of electromagnetic phenomena, um, it's sufficient for us to just confine ourselves to the case of only one potential non-zero and all the other potentials zero and just see what happens in that case. Okay, so I guess that's it for today. Thank you.